Okay, welcome back, everyone. Hope you had a good weekend. I believe I sent out, before the end of the week, I sent out another mini exam, and you should have received that through Canvas email. And I believe the due date on that, if I'm not mistaken, is a week from today. So it's kind of a short timeline on that one, if you're going to be interested in doing that one. And hopefully by the time we get through this week, you should have what you need for that exam. I'll double check when we get to Wednesday to make sure that you have everything for that exam. All right. Any questions before I start? Good. Okay, we ended last class. I put you in breakout rooms and had you look at this problem of trying to find the volume of a solid that was below a sphere and above a cone. And I hope that from that example, we saw that how the region of integration that I guess you could look at like the let me see, I'll just put it up here. It wound up being this thing that looked like an ice cream cone kind of. And so the region of integration on the ground wound like the shadow, almost looking like a projection of this solid down to the XY plane, wound up being a disk. And so the region of integration on the ground was perfectly suited to become a polar region because it looked like this. So that's what we ended with last time. And what we want to do now is look at a kind of a different sort of perspective on our regions. So if you go back and look at when we first started talking about polar regions, we said that a polar rectangle would be where you have your radius and your theta restricted between two constants. And anytime you restrict your theta and your radius between two constants, you get a shape that would look something like this. And as you adjust your radius, the restrictions on your radius, you might change the outer limit and inner limit of the wedge that we're creating. And then if you change your theta, then you change just the angle, right? So we have that's what a polar rectangle looks like. But if you go back to, when we first started talking about double integrals, we had type 1, type 2. I think I summarized it here in the beginning. Yeah, so back when we were doing Cartesian, we had a regular Cartesian rectangle where our x's were between two constants, our y's were between two constants, and then we had a type 1 and a type 2. And the type 1 of our variables, x, was trapped between two constants, but our y variable was between two functions of x. And then in type 2 was reversed. Our y's were between two constants, and here our x's were between two functions of y. So since we have talked about a polar rectangle, right, which would be the polar version of this, we need to ask ourselves, is there kind of like a type 1, type 2 region in terms of polar? So there is, and we're only going to talk about like a type 1. We're not going to look at the type 2. So that's where we're heading to right now. I just want to kind of give you kind of a brief recap of what we had done before. So let me get to where we are here. So if we have a double integral over a polar region, we're now going to consider what's called a type 1 polar region. Okay, this is polar, but it's very similar to the type 1 we had from Cartesian in the sense that our angle, our theta, will be stuck between two constants still. Okay, so the angle that we use for the polar is stuck between two constants, but the radius is no longer stuck between two constants. Instead, it's stuck between two functions of theta. Now, this is something that you would have looked at the end of Cal 2, but I know not everybody gets to it. So I'm just going to step away from this right now, and we're actually going to look at what a function of theta looks like. All right, so take you back to Cartesian. If we say that y is a function of x, then we can visualize a function of x by putting the input and output on the x and y axes. If you go out a certain distance x, you plug that into the function, it's going to spit out some y value, and that'll be the height of that point. So if you take all the inputs and all the outputs together, you get the curve. Now what I'd like for you to consider is this. A function r being some function of the angle theta. Okay, so this is a polar function. And so the input is the angle and the output is the radius. Right, so I'm going to give you a very simple, let's do a simple example first. So let's say I define a function r to be equal to 3. So r is some function. In this case, it's not really a function of theta because theta doesn't appear over here, but this is a constant function. Would you all agree? It's just always 3. And this is saying that your radius is 3 all the time. So what would this draw?
Just a circle of radius 3.
Circle of radius 3. So the equation for a circle of radius 3 in polar coordinates is very simple. It's just r equals 3. Compare that. What would the equation of this circle be if we had to do it in Cartesian? Right? In Cartesian, it would be x squared plus y squared equals 9 squared. Or sorry, 3 squared, which is 9. Right? That would be the same. That would draw me the exact same thing as this, but the equation is much more complicated. And if I tried to solve it for y, I would wind up getting like y equals plus or minus the square root of 9 minus x squared. I would actually get 2 different curves, right? It would be much more complex in the Cartesian system, but in polar, it's very simple. Make sense? Okay, no questions, we're good? Let's look at something that's not so simple. We're actually put a theta in here. So how about if r equals, well, let's just do theta. What would that draw? So it might help if we do a t-table. Good old-fashioned t-table. Here's some values of theta. Here's some values of r. So let's start with 0. If I plug in 0, then the radius is 0. So let me draw that point. So theta is 0 means that I'm going to start by pointing out, like it's like you're standing at the origin and you're just standing there looking out the x-axis, right? That's 0 degrees. And how far am I supposed to walk out? 0, right? The r is how far you walk. So I'm just going to stay where I am. So that point is just right there. Okay, that's that point right there. Now let's do a different angle. How about pi over 4? That's 45 degrees, right? So now I'm going to turn. I'm going to aim like I'm looking this direction, 45 degrees. And how far am I going to walk out? Well, same distance, right? Pi over 4. So we get on our calculator, we do pi, right? Divide that by 4. It's about 0.78. So I'm going to walk out about 0.78. I don't know, I'm just going to say that's 0.78. And that's the distance from here to here. That's pi over 4. Understand? What if, and I didn't do this one, but what if I had done pi over 6? I would have walked out pi over 6, right? Which isn't quite as far as pi over 4. So if I were facing pi over 6, I wouldn't have walked out that far. So I would have been, I don't know, somewhere around here maybe. Anyone see what it's going to draw now?
A spiral?
Maybe a spiral. So if I do, let me do one more. If I do, let's say pi over 2, right? Now I'm facing straight up and I'm walking out pi divided by 2, which is pi divided by 2, 1.57. So now I've walked out to, here, let's say. So if you were to connect, if you were to do all the possible thetas in here and all the possible r's that come out, you would start drawing this spiral that would just get bigger and bigger and bigger as you keep aiming at different angles. That all makes sense? Yeah. Okay, we'll do one more. the right-hand side can be any function of theta. So how about I do like sine of theta? So I just made that up. I mean, it could be anything I want, but I'm just going to make that up. Okay. So let's see what this draws. And I'm going to do a t-table again. I think t-tables are the easiest way to do these. Okay, so if I have 0 here, well, sine of 0, 0, so I will be here. So that's going to be the origin. Now let's just take our time through this. Let's aim out pi over 6 now. So if we do pi over 6, what's sine of pi over 6?
It's 1.
Just 1? Sine of pi over 6?
1/2.
That's 1/2.
1/2, 0.5. So that means I'll go out 1/2. So that means, I don't know, I'm going to just say that this is 1/2. Okay, I'm just making that up. That's 1/2. That's the distance from here to here. Okay, is 1/2, 0.5. Now let's aim pi over 4. So if I go pi over 4 here, sine of pi over 4 would be root 2 over 2, right? Which is about 0.707. So it's going to be further out than this, right? So I'm going to be about here now. Okay, now it's not going to be a spiral this time. Let's keep going around. Let's pick another point here. How about pi over 3? So sine of pi over 3 is root 3 over 2. And that, just so I get a nice exact answer, square root of 3 divided by 2.0, about 0.86. So it's even further out than that last point I just drew. So not much further, but it's a little bit further out. And what about when I get to pi over 2? Sine of pi over 2 is 1, right? 1. So now when we're pointed straight up, we should be 1 unit up. Okay, y'all with me? Okay, now I keep going, right? Where am I? Pi over 2. Let's go, how about 3 pi over 4? That's like kind of the next important one. I don't want to do every single important angle. I'm just going to do a couple of them. So sine of 3 pi over 4, isn't that also root 2 over 2? So 3 pi over 4 is pointed this way, and I need to walk out the same amount that I did here. So I'm going to be about right there. And then what about when I get to pi? What's sine of pi? 0, right? So now we're at 0. So we're back to the origin. So here's what is drawn so far, and this is going to be just my very sketchy drawing. It's like this. Okay, y'all kind of with me on that? Now, pay attention to this one. This one is a little tricky. What if I go to here? What angle is that? We go around to here. What's that angle? From here to here.
Seven pi over 4.
7 pi? I think you're thinking of this one.
5 pi over 4.
5 pi over 4. Yep, 5 pi over 4. And then what is sine of 5 pi over 4? Well, negative root 2 over 2. We're getting a negative answer. So think about this. You're standing at the origin and you're looking in this direction, right? And how far are you supposed to walk out? Negative root 2 over 2, which means you're actually going to walk backwards. And that's going to put you backwards right at that point again. And if we keep doing this and we aim this way, let's say we aimed it straight down. That's 3 pi over 2. And sine of 3 pi over 2 is -1. So it's like we're facing that way, but we walk backwards 1, and it's going to put us back up here at this point. So guess what? Between 0 and pi, it drew this thing in green, didn't it? And then as I continued past pi, it continues drawing the same thing again. Do y'all see that? It's just going to draw it again. And when I get back to 2 pi, it's just going to draw it again. So would you all agree with this? This right here, r equals sine theta, draws this green thing as long as my theta is between 0 and just pi. Right? If I just go between 0 and pi, it's going to just draw one of these things. If I keep going past pi, it'll just draw another one, and another one, another one, another one. Understand? Now, this shape, what does that look like? It looks kind of like a circle, right? Kind of. I wonder if it is. I wonder if it is. Maybe we can figure this out. Is that a circle? Well, let's take our equation, right? Let's take our equation, r equals sine theta. And let's think about Cartesian. So we learned last time that when it comes to polar, we had these conversions from Cartesian. Here they were, right? These were our what do you call it? Our conversions. Let me just grab these. I'll take these over here with us. So if I take this, come on. How can I convince myself that this might be a circle? All right, well, here's one thing we could do. Look at this. Do you all agree that y is r sine theta? Yes? So you could solve that for sine theta and get that that is y over r, right? So let's take this equation. Now this becomes r equals y over r. Yeah? And then what would, if I multiply both sides by r, I would get r squared equals y squared, right? Agree with that? Just multiply both sides by r. Are y'all following me so far? Okay, so now from what I'm trying to get at, let me tell you what my goal is. I'm trying to get at this right here. Trying to see if there's any way I can convince myself whether or not this is a circle or not. So I have that r squared must be y squared, which would be this, but would that be a circle?
That's a parabola.
Looks like well, yes, but see, we would need this to be like x equals y squared or something like that for us to say parabola. So let me see, is there something else we can do? How about this? Let's keep this on the back burner for now. Let's take this equation again and let's square both sides. You agree with that? Okay. So r squared is sine squared theta. What's another way we can write sine squared theta using the Pythagorean identity?
1/2 plus 1/2 sine theta.
Oh yeah, okay, so you're doing like a power reducing formula. I was going to say something more like just 1 minus cosine squared theta, something like that, right? That's true from the Pythagorean. Yes. Okay, what is cosine theta? If you take this formula, what's cosine theta? Solve for cosine theta. What do you get?
X over R.
X over r. So we have r squared equals 1 minus x over r squared. I'm running out of room. Hold on. Got to go to a new page. Give me a moment. Okay, now if we clean this up or work with this algebraically, this becomes 1 minus x squared over r squared, right? Let's clear the fractions. Let's multiply everything by okay, so I multiply everything by r squared there. Are y'all following me? Yeah,
Kind of.
kind of. Okay, I'm just trying to see, is there a way for us to go from this, from the original polar equation, r equals sine theta, and somehow figure out, is that a circle? Right, is this a circle? I mean, does that look like a circle to you or no? Doesn't look like a circle?
Kinda.
Kind of, maybe. Let's continue with this and see if we get ourselves stuck or if we get to an answer here. What could we do here? If r squared is y squared, I could replace that with y squared, couldn't I?
Oh yeah.
Using this. Okay, still not a circle yet. This really is, let me see. Yeah, this is what, how could I rewrite r to the fourth using this equation? Couldn't I do x squared plus y squared equals y squared minus x squared?
Yeah.
Right? I could do that. See, there's so many different ways we could go with this. It starts to look, it starts to look challenging to come up with an equation that's going to give you, go ahead.
Sorry. Is it a circle if you do r to the fourth plus x squared equals y squared? Like switch that around, or is
Wait,
that
say it again.
on the second to last equation where it says r to the fourth, could you switch x to the other side? Where it'd be r to the fourth plus x squared equals y squared. Is that a circle or no?
Well, no, because a circle for us is always going to look like what's in yellow here, right? It's always going to look like this, right? So we need x squared plus y squared equals r squared. That you would have x squared plus r to the fourth, which isn't a circle.
Oh, okay, I understand.
Okay, I'm going to keep going with this to see what happens. This right here, if I expand this, this is x to the fourth plus 2x squared y squared plus y to the fourth equals y squared minus x squared. Okay, this is starting to look like a disaster, isn't it? Isn't it starting to look like a disaster? Okay, so is there a way for us to convince ourselves whether or not this draws a circle or not? There is. Okay, there is a way. I'm trying to illustrate to you that there's not, it depends on what path you go here as how easy or hard this is. So I'm going to try and ask you to consider this a slightly different way. If this were a circle, if it was, what would its center be? What does it look like its center is?
1/2.
Right there, right? That point?
Yeah.
What's that point? What's the x coordinate?
1/2.
0 for the x coordinate, 1/2 for the y. Now, does everyone understand we're going with 1/2 because from here to here is 1, right? So this would be halfway. And then what would the radius be? It would have to be a half, wouldn't it? That would be our radius. So if this is a circle, if it is, then from knowing that the center would have to be this and the radius would have to be this, we would know that the equation of our circle, right? So I'm going to stop here. If it's a circle, it has a center of 0, 1/2, and it has a radius of 1/2, which means the Cartesian formula, right? The Cartesian formula would look like this. Remember, this is the general equation of a circle. This is the equation of a circle. that's centered at HK, right? This is centered at HK. So for us, it would look like this: x squared plus y minus a half squared equals 1/4. You all still with me? Okay, this is x squared plus y squared minus y plus a fourth equals 1/4. Okay, so all I did there is squared this. Still there? Okay, the 1/4s cancel. And we get x squared plus y squared minus y equals 0. Now let's go to polar. Whenever you do polar conversions, x becomes r cosine theta, y becomes r sine theta. So I'm going to convert everything over now. X becomes r cosine theta, so I'm going to square both of these. So I square the r and the cosine. Plus, now I take the y, which is going to become r sine theta, and square both of them. And then I'm going to take minus y, but y is what?
R sine theta.
R sine theta.
R sine theta equals 0. By the way, this x squared plus y squared, I could have just used this conversion right here. X squared plus y squared is r squared. But I wanted to illustrate that if you do just replace them, you can factor out your r squared. And you'll be left with the 1 there, right? When you pull an r squared out of both of those, sine squared plus cosine squared, then minus r sine theta equals 0. So here's where we are. R squared minus r sine theta equals 0. Almost there. Factor an r out. And now you have two things that multiply to be equal to 0. So you set them both equal to 0. R equals 0, or r minus sine theta equals 0. And if I isolate r by itself here by moving the sign to the other side, look what we have.
Oh, so it is a circle.
It is a circle. Because what we're saying here is that if you take a circle in Cartesian, you can always convert it over to its polar form, and then you'll get an equation. And basically what it's saying is, for this to be true, like from Cartesian to polar, is that you're either going to have r equals 0, which means you have no circle at all, right? No radius. Or you're going to have this polar equation, r equals sine theta. And that's exactly what we started with. So believe it or not, r equals sine theta draws you a circle centered at 0, 1/2, and has a radius of 1/2. I hope that makes sense. It's weird, but you know, it is what it is. So I'll leave it to you as a challenge to see if maybe you can figure out a way to go from here to here. It can be done. You just got to pick the right algebraic path. I went the other way, right? I just showed you that that equals that. But here to here, that's open question. Okay, so the last part of this section says that, all right, well, if you're not looking at a polar rectangle where both the theta and the r are stuck between constants, and instead your theta is stuck between two constants, but your r is stuck between two functions of theta, then you wind up drawing a polar region that looks something like this. So notice here on this picture, your angle that you aim, right? Remember, you stand and you point out alpha first, because that's this lower restriction. And you're only allowed to look between alpha and beta. And then the radius, which is how far you walk out between alpha and beta, like the distance you walk out, is always stuck between two functions of theta. Then you're going to get some weird polar region that looks like this. So the question becomes, how do you do a double integral over a region like this? Well, you do it the same way you did a type 1 back with rectangular or Cartesian coordinates. That is, you set up your double integral. Inside you have a function where your x gets turned into r cosine theta, your y gets turned into r sine theta. You always have to include that r. Remember the very important r that always comes into play whenever you convert to polar. And then you have to go dr d theta, and you have to use this order where d theta is the outside integral, and that's because the restrictions on theta are between two constants. And then r is the inside integral because that restriction is between two functions. So the one that's restricted between two functions always has to be the inner, and the one between two constants always has to be the outer. All right, let's see this in an example. Are you ready to do an example with this? This is just to kind of get you to get a feel for what we're trying to do. And we're going to start out with one of my favorite problems. All right, a sphere of radius 3 has a cylinder of radius 1 drilled out of it as shown below. So we're going to take a sphere that has a radius of 3, and we're going to drill out a cylinder out of it, okay, where that cylinder has a radius of 1. Now let me draw a picture first before I show you the picture, because it says as shown below, right? I haven't shown you the picture. Right now, here's what you might be thinking. Here's a sphere. Radius on this is 3 for the sphere. And then you have a cylinder that we're going to drill out. So maybe you're thinking a cylinder that we're going to drill out of this, where the radius of this is 1. Does that kind of make sense? And we want to know the volume of what remains. Okay, understand? Now, this is not an easy problem, because do y'all see when you drill this out, this top part, when you drill this cylinder out, the part that you drill out actually has a little cap on it, like a little dome on the top. And then on the bottom, when you drill that out, it's going to have like a little dome on the bottom also. Right. So in other words, you can't just find the volume of the sphere or the ball. You can't just find the volume of that and then subtract from it the volume of a cylinder, because this is not a true cylinder, because the top of it's a little curved and the bottom of it's a little curved. You all understand that? So it's not as simple as it seems, but this isn't even the problem I want you to do. Okay. Ready to see the picture? Here's what I want you to do. I want you to find the volume of this sphere. I don't want us to drill it out of the center. I want us to drill it off-centered. That's even more problematic. You'll see that? Because there's not even the symmetry we have. Now here's kind of a picture of it, a different picture. We have this sphere here, or ball, and we're drilling out the green, right? The green is what we're drilling out. But when you look at what's actually drilled out, let me see here. Let me pull the cylinder out of here. Where's my? Just gonna look at the top half of what we drilled out. The part that we drill out right there. Now remember, there's another part on the bottom here. I'm just showing you the top piece. This illustrates that we have that little dome on top, right? This little cap that causes an issue. Right. So we need to try and figure out if we can do this. All right. Does everyone understand the problem? All right, so the way we're going to do this is first, let's try and figure out what coordinate system we want to use. So when we look at this solid, when we look at this thing, if we're trying to find the volume, let's try and find the volume of this. You know what? Let me illustrate this way. Do you agree with this? The volume of the sphere, or I'm going to say the ball, okay, whatever that volume is, minus the volume of the part that we drill out is equal to the volume that we want, right? That's what we want. Okay, the volume of the ball. Can we all find the volume of the ball without doing any calculus?
Yeah.
Sure, we have a formula for the volume of a ball, right? That we can look up, it's not a problem. So this, no problem. Okay, really the problem becomes, can we find the volume of the part that we drill out? That's the question. So a double integral, I should be able to find this volume. If I look at the top cap of this, let me do this in a different color. If I look at this top cap, which remember, it has a little curve to it, right? If I look at that as some surface on top, some function of X and Y, that's my top cap. And then I'm only gonna look at the bottom of this. I'm only gonna look at half of it, okay? And then what I'll do is I'll double my answer, all right? So we need a bottom surface, G of XY. And then what we'll do is we'll do a double integral over whatever the region is on the ground. Now the region on the ground is gonna be this little thing on the ground. That's my, kind of like my shadow of this solid onto the XY plane. So if we call that thing, let's say D, then it's the double integral over D of the top surface minus the bottom surface with respect to area. And to get this answer, I actually need to double it, because remember, this only gives me half of it because I'm going to go down to G, which is just the halfway point. That'll make sense. Yes. All right, so I'm gonna copy this.
I'm
Let's
a little
take
confused. What is G of X and Y?
a top surface and a bottom surface of the solid we're trying to find the volume of.
No, like I understand it's a bottom surface. I don't understand what surface we're looking at.
Oh yeah, yeah. So that's still the open question is what are those surfaces, right? Like what are they going to be? So let's go ahead.
I was gonna just say, like, in my head, all it looked like is we just need a f of X to be a hemisphere, and then we just calculate over the region of D. I didn't really see a need for G of X of Y.
Well, that's right. We won't need G of X of Y because it's the ground, right? Oh man, it didn't copy that. Okay, hold on. I think I can get that all back.
Control Z.
Yeah, hold on. There we go. Let me do something here. Okay, there we go. So I want to copy this. Yeah, G of XY here, right? G of XY is just the XY plane, which is Z equals 0, which means this is really going to be 0, which means all you need is f of XY. Is that what you're saying, Daniel?
Yes.
Yes, that's exactly right. Because of the geometry of this particular problem, and because I've chosen to only do half of it, right? And just double the answer, then yes. That's why I'm not going to do the whole thing. I only want to do half because it'll be easier.
Okay, the G of X of Y was just very misleading for me at the moment.
Okay,
But
I'm trying to illustrate why we're using, this is like the generic formula. Without the two, this is our generic formula. So if we want to find the volume of a solid, we need to know the domain it's over. We need to know the upper surface and lower surface and then subtract these two. That's the general formula. In our case, G of XY is 0. So
works for me.
okay. All right, now I need to bring the problem back up here. Well, all you're given is that, well, let's try and get this. The sphere, right? What do we know about? Do you want to start with the domain or you want to talk about the surfaces first?
I say domain.
Let's do domain. Okay, because the domain is going to be the thing that pushes us to polar. Because at this point, nothing is telling us polar until we get to the domain. Oh, and you know what? On my picture, I don't tell you, the only thing about this picture that you need to understand is that our circle is running tangent to the z-axis. See that? Our cylinder. So we're keeping our drill bit so that the edge of the drill is always touching the z-axis. It doesn't matter where it is, as long as it's touching the z-axis and always runs tangent to it. So when I'm setting this problem up, I'm going to choose to orient it in this manner. I'm going to choose to orient it so that my domain, let me get up here. I think I'm going to orient it this way, where this will be my x-axis and this will be my y. That's just going to be the choice that I make right now. Okay. You could, if you wanted to, choose to do it this way. And you could actually use the polar region we just talked about. The polar region, didn't we just draw this thing a second ago? with r equals sine theta? It was close to this. It wasn't exactly this, but it was pretty close. Yes. But I'm not going to do that. I'm going to give us one more problem where we have to actually think about this. So I'm going to choose to orient it this way. So this is going to be what I use to draw my domain. In fact, I'm just going to grab this and take it over here. So talking about domain right now. Okay, my domain D here. Well, I'd like that to be in polar, right? I'd really like to convert that to polar. It's perfect for polar, right? You wouldn't want to do that in Cartesian because it's not a type 1 or a type 2, and it's definitely not a rectangle. So if I'm going to go to polar, the way I'm going to start is I'm going to realize that this is a circle that has a certain center and a certain radius. So do we know the radius of this thing that we're drilling out?
1.
Didn't they say it was 1? Okay. So then do we know its center?
0 or 1 0.
So yeah, if the radius is 1, you look at it this way. If the radius is 1, here's the center of the circle. The radius is 1, then we know that the distance from here to here is also 1. And so that would be the point 1 0, right? So this would be x minus 1, y minus 0, and then the radius squared. So end of day, this is just x minus 1 squared plus y squared equals 1. And then I'm going to just do the same thing I just did a second ago. I'm going to expand out the left side. X squared minus 2x plus 1 plus y squared equals 1. And then watch what I do here. I'm going to go a little faster this time. X squared plus y squared, that goes straight to r squared, doesn't it? When I go to polar. So here I go to polar. That's r squared in yellow. Minus 2. Now x gets converted over by turning into r cosine theta. And then the 1s are gone. So equals 0. Everyone understand where that came from? I'm going to factor an r out. And I'm going to set each of these equal to 0. I get r is 0. And r is 2 cosine theta. Questions?
What happened to the y squared again?
X squared plus y squared. This in yellow, using the Pythagorean identity. This one right here. X squared plus y squared is r squared. That's the polar conversion that we have. Anytime we go from Cartesian to polar, we can use that equation. And that's what we're doing. X squared plus y squared, I replace it with r squared.
Oh, okay.
And then minus 2 times x gets replaced with r cosine theta, and then the 1s cancel. Okay, so let me see if this all makes sense now. I'm gonna focus our attention on this right now. If I were to tell you to make a t-table, make this theta, and then make this r, and start drawing this, let's see what happens. If theta is 0, what's cosine of 0?
It's 1.
1, then times 2, so we get 2 here. So when we're pointed out this direction, we want to walk out 2, so that puts us here. And then let's say we go to pi over 4. That'll be, let's see, cosine of pi over 4 is root 2 over 2. So root 2 over 2 times 2, that should give you root 2, which is about 1.4 something. So now you're about, I don't know, somewhere in here. Let's go to the next nice angle, pi over 2. Let's see, what's cosine of pi over 2? 0, right?
0.
Okay, so this gives us 0. So now we're back here. So believe it or not, between 0 and pi over 2, we actually draw the top half of this circle. Oops, that's terrible. And then if I go and keep going around, Let's see, let's do the next important angle, which would be this one right here. It's 3 pi over 4. So what is cosine of 3 pi over 4? So 2 times cosine of 3 pi over 4 is negative root 2 over 2, which gives you negative root 2. So when you're facing out this way, right, out that way, you actually have to walk backwards, and it's going to put you at a point right here. It's kind of, sorry, it's right here. It's kind of in line with this one. And then when you get to pi, when you plug in pi into this, cosine of pi is 1, so times 2, you get 2. So now you're back to here. So you wind up drawing, I'm sorry, -1. I'm sorry, -2. I should have said -2. Cosine of pi is -1, then you hit it with 2. So you're facing this direction and you walk backwards 2, which puts you back here. Why is this part important, what I'm doing right now? Why is this important?
To find out the domain.
It's domain, but specifically, why did I have to do this table here?
It gives us the restrictions on theta.
Exactly. See, we can't go 0 to 2 pi on theta. If you go 0 to 2 pi, it draws 2 circles. I only want to draw 1 circle. So I know that I can do that between 0 and pi. It goes and it starts here and it goes all the way around. Then you start, doing backwards and you wind up drawing the whole circle. So from this, I know that my theta has to be restricted between 0 and 2 pi. I'm sorry, 0 and pi, I just said 2 pi. Okay, that's my restriction on theta that will draw that circle. And now my radius, this is another tricky part. This right here just draws the outer edge, doesn't it? Of the circle. So like when I was facing out this direction and I plugged in pi over 4, it took me to that point exactly. But I want everything in between. I want everything between here and here. Just like when I'm at this point, I want everything between there and there. This point, everything between here and here. And that way, as I go around, I start filling in this circle. And then when I go backwards, I start filling it in like this. And I get this actual disc on the ground. So my radius must always be, as an upper bound, be this curve. And a lower bound be 0, which is what gives me all the points between that edge and back to the origin. This is it right here. This makes up our domain, D. Now's a good time for questions if you have them. So we're okay? All right, so we have a polar region. We have a restriction on theta. Theta is between 2 constants. The radius is between 2 functions of theta. This is a function of theta. 0 is really not a function of theta, but you could say it is, even though it's a constant function. But the radius is definitely not between 2 constants, right? It's between 1 constant and 1 function of theta. So I have to treat this almost like a type 1, which means I have to do what this note was all about, which was if your radius is a function of if your radius is between 2 functions of theta, then you have to do your integral this way, right? Okay. I think I need to start a new page here. So I'm going to use this formula now. Now we need to find the upper surface. What is the upper surface? So what was the f of x, y? What was the top one?
Part of that.
The upper surface is part of the sphere, isn't it? And that means you need to know the equation of a sphere. Do you know the equation of a sphere? Well, we know that it's x squared plus y squared plus z squared equals r squared, right? That's the equation of a sphere that's centered at the origin. Do we know the radius? Wasn't it 3? So for us, it's x squared plus y squared plus z squared equals 9. And can we solve this for z?
Yeah.
Yes.
Sure. Move everything over first. And we can take the square root. And we only need to consider the top. Why do I only need to consider the top, right? The plus gives you the top of the sphere, the minus gives you the bottom of the sphere. So I'm only going to look at the top part because that's all we're looking at. So that's what f of x, y is. Are there any questions on that? Where I'm getting that from?
I have a question, actually.
Yep.
So our equation of a sphere that we are currently using is in Cartesian coordinates, but we are looking to solve this with a region in polar. Is that going to create any type of conflict? Will we have to convert one to the other, or?
Yeah, good question. Yeah, that's what we have to do. In this formula, this is like the Cartesian generic formula. But when you go to polar, your function, instead of x and y, you have to replace x with r cosine theta and replace y with r sine theta. So that's what I need to do now. I'm going to say, all right, what is this function converted to polar? So I'm going to do that. I do also want to figure out what the g function was, though, before I do that. So g of x, y was the bottom one. And we had already talked, that's just the ground, that's the xy plane, so that's just 0. So now let's go to polar. This thing to polar. So what looks like the easiest thing to do there?
Plug in r cosine of theta for x and r sine of theta for y
Yeah.
and
you
call it a
could-
day.
Yep, call it a day. I think I have one even faster than that. Why don't we factor out a negative from both of those? And then just replace that with r squared. You get the same thing, right? You get the same thing. Okay, you with me? We're getting close. We're actually getting real close here to setting up the integral. Here it comes. We want to do the double integral. We want to go from 0 to pi. Those are our restrictions on theta. That'll be my outer integral. Then I want the top function, which is the square root of 9 minus r squared. Very nice and clean function. Minus the bottom function, which is 0. I don't need to put that. I'm just, again, illustrating that this is the top cap of the part we're drilling out. This is the bottom cap. And then what comes next?
RDR.
R dr. Okay, don't forget you have to put an r here times dr. And that r comes from the fact it will always be there. Always, always, always be there if you convert to polar. Don't be the student that forgets that, all right? So, and now I need my limits of integration. I didn't put them here. I was waiting here. So my inner integral has limits of integration of 0. And what was it? 2 cosine theta? Wasn't that it? That was the restriction on r, wasn't it? From 0 to 2 cosine theta. So a totally cleaned up integral would look like this. Can you integrate that? Look at your inner integral. Can you handle that integral? How are you going to solve this? If you
U
had to
sub.
do that, U sub. That's a pretty basic integral, right? If I had to do that over here on the side, just do a quick U sub. Let's let U be equal to 9 minus r squared. Then du would be negative 2 rdr. I have an rdr, so I can scale by negative 1/2 on both sides. This is Cal 2, so I can't take too much time on this. This integral becomes negative 1/2 integral of square root of u, which is same as u to the half, and then du. That's just a basic u sub over here. Now I do the antiderivative. I get -1/2 times, see, I add 1 to that power, that gives me 3/2. So I have to put a 2/3 out here, use the 3/2 plus some constant. 2's cancel, I get -1/3 u, which is 9 minus r squared to the 3/2 plus c. Okay, so that's my Cal 2 life, right? Coming back to me here. And so that goes in here. So here we go. This becomes integral 0 to pi. Okay, now I'm going to take -1/3 9 minus r squared raised to the 3/2. Evaluate that from r equals 0 to r equals 2 cosine theta, and then d theta.
I have 2 questions.
Yes.
Is it me or did you just forget to multiply by 2 the whole integral? The whole double integral? Because right now we only have the upper region of our drill
Yeah,
bit.
this is just going to give us the volume of half of it. I have to go back and where was that page? Oh man, where is it?
Somewhere in there.
Somewhere in here. Well, you know what, was it here? Yeah, here. So remember, I'm only doing this integral right now.
Mhm.
When I come back to this, I'll have to do double of that, right? To give us this.
And
So
my second, I'm sorry.
This is everything we're doing right now is just this part right here.
And
Okay,
my
let's
second
go.
question was gonna be, weren't we only supposed to set up the integral?
Yeah, so at this, well, now you're going to see why, okay? Because at this point, remember what we have to do. We have to replace r with 2 cosine theta. That goes in here. And if I square that, I'm going to get 4 cosine squared theta, but then all of that raised to the 3/2, that you're not going to be able to integrate. Okay, which is why in the original problem, I said, do not evaluate. Just set up the integral, okay? Which yields the volume of the remaining solid. So to have a final answer that is correct, here's what we would have to have, right? So we don't have a final answer yet, but I think I can just throw it right here. And I'll go back to my notes. Here was the integral that gives us that integral right there. You know what? We'll do this one. This integral right here gives us the volume of half of what we've drilled out, right? Half of what we drilled out. We want something that's going to represent the volume of everything that's left. So I'm kind of ready for my final answer now. Try and squeeze it on to one page here. All right, so the volume will be, first, the volume of the whole ball. What's the volume of the whole ball? So what's the volume of a ball?
4/3 pi r cubed.
4/3 pi r cubed. Okay, so I'm going back to this one. This is the volume of the ball minus the volume of what we drill, right? Is the volume of what we want. The volume of the ball is 4/3 pi times the radius, which we know is 3 cubed. Okay, so this, I understand this becomes 27. You can reduce this, but I'm just trying to illustrate again. This is the volume of the ball. Now the part that we drill out. We need to double the double integral. Well, this right here, 0 to pi, 0 to 2 cosine theta, square root of 9 minus r squared times r dr d theta. This is the answer. That computation will give you the volume of the ball that's left when you drill out the way we drilled out. All right, what do y'all think? This integral we could do on a computer. I actually think I did it on my computer. Hold on, let me see. Yeah, so I did this. I already had it do it for me. And when I did that, I got 17.1639. And then I did the volume of the ball itself, which was 36 pi. And then I took that answer and I asked the computer to subtract 2 of those integrals. Oh, wait, hold on. No, here's the whole thing. This is everything. So this is the volume of the ball. And then I'm subtracting 2 of those integrals right there. And I get 95.93. So you're not supposed to do this work. I'm just showing you that we actually have the volume of that. All right, so hopefully that shows you how polar coordinates can be somewhat useful, all right? In the sense that you can find the volume of some very strange objects that way. All right, now the next thing on our schedule, if you look at what we're supposed to cover, the next thing on our schedule, we jump from here, double integrals over polar, that's right here. We're supposed to go straight to triple integrals, but I'm going to take a slight detour and talk about 12.4, which is applications of double integrals. And I really need to take a quick break. Thought I'd be able to make it to end of class, but give me a second. Just kind of hang tight. I'll be right back. Okay, sorry about that. So applications of double integrals. I'm not going to go in depth through this, okay? There are some examples in this that I'm not going to do. And the only reason I'm showing this to you is because on the mini exam, this comes up. So this is one of those things where it's a topic that I want to at least expose you to a little bit, but I'm not going to go through any examples. I think it's pretty, well, I don't know. We'll see what you think. So these are just some applications of double integrals, namely how we can use them to find the centers of mass of non-homogeneous laminas. Okay, so all that means is, let's say that you have some, some shape, let's say it's not a rectangle. I don't want to tear this up. Let's see if I can do this without making a mess. Okay, so let's say that I take some weird random shape. Take some weird random shape like this. And let's say I want to find its center of mass. Well, if it's homogeneous, that means if the density of this thing is uniform, which we could assume a sheet of paper is pretty uniform density, then it's actually kind of easy to find it. You can do it physically by just taking a little pin and hanging this from the pin and drawing a line straight down, like dropping a plumb line straight down. And then taking it from another position and doing the same thing and hanging it and drawing a straight line down. And if you do that, where the two lines intersect is your center of mass. So at that point of intersection, I should be able to balance the sheet on that where those two lines intersect. It's pretty easy if you have a homogeneous, but if it's non-homogeneous, then it's harder. So what does non-homogeneous mean? It means that we have a specific lamina, some sheet, that at each point, the density is different, Okay, so maybe over here your mass is more, you have more mass per square inch than you have over here. You know, and over here it's different. So basically the density at every point depends on the point. And that's what this is all about. This is saying, suppose you have a lamina in the XY plane where density is mass over area. That's just a physics equation. Density is mass over area. Then if we were to cut this lamina into infinitesimally small patches, then, oh, and sorry, I forgot to mention, and at each, let's say that at each point, so at each point in here, I have some density function. So this is rho of xy. So instead of like f of xy, we're just called rho of xy, where that, at that point, once you tell me the x and the y, I'll tell you the density at each point. Okay, so we have to be given some density function. So if you give me a density function, then what I do is I take an infinitesimal little patch like this, okay, and I know the density at that point, okay, I know the density from the rho function. Then dA, right, which is going to be this times this, okay, it's basically the area of that little patch. If we take, stop it. If we know that density is mass over area, then that means that mass is density times area, right? That just multiply both sides by area and we get that mass is density times area. And if the density is given to us by our rho function and the area is dy dx, then the mass at that little infinitesimal patch is just going to be those things multiplied. And if we want to know the mass of the whole lamina, we need to add all these up. And we already know how to add a bunch of things up. We just use a double integral. So that's what this formula is saying. That's what's up here, is that if you want to know the mass of the lamina, you just do the double integral over the region D. The region D is the actual lamina itself. In the integral, you have the density function and you integrate that with respect to area. So the double integral can give you the mass of the lamina. Understood? Okay, sure. Now, you could change this completely away, take it into a completely different physical situation. Instead of me talking about mass, we could say that we have an electrical charge at each point on a lamina. So instead of me saying, hey, I'm going to give you a function that gives you its density, I'm going to tell you, here's a function that gives you its electrical charge. And then what you could do is you could figure out the charge density, okay, and then same computations, basically, the double integral over that region D, integrating this time the sigma function, sigma of xy, just some function that gives you the charge density at each point. This will give you the total charge on the whole lamina. So I'm just trying to illustrate to you that the double integral, you know, what we've learned in this section, the double integral over some region D of f of xy dA can have very different physical meanings. It could give you the mass of a lamina, it could give you the total charge on a lamina, and in different, you know, fields, it gives you different things depending on what it is you have in front of you. What really, it all depends on what that function is. If it's a density function, you got mass. If it's a charge density function, it gives you total charge. So let's see if we can't do, like, I'm not going to do the problem, but I'm going to at least maybe set it up. So lamina, let me see if I have the picture for this. Yeah, I don't. Okay, I thought I did. Okay, so a lamina is formed by the region bounded by these curves. I'm going to take this onto a new page. Like I said, I'm not going to do the whole problem. I just want to at least get us set up so you can see how this works. So lamina is formed by the region bounded by these curves. The density at xy is given by this density function. Find the total mass. So I already know that the mass is equal to the double integral over the region D of the density function dA. That's what this section, starting out this section, that's the big first formula. And so I just need to figure out what this region is. Okay, so let's take a look at this region. All right, let's start with y equals 1 minus x. That's let's say that that's 1 unit up. This is a line that has a slope of -1, so it goes down like that. Oops, I missed. And that's also 1. Then I have y equals 1. Y equals 1 looks like this. And then I have x equals 1, which looks like this. And so the region we're talking about is this region in here. So that's my lamina. And the density at any given point, so if I take a point here, x, y, then if I want to know the density at that point, I just take the x coordinate and multiply by the y. Right? So it's non-uniform. It's non-uniform density. So what type of region is this? If this is a D, what type of region? Do you want to do Cartesian, polar? Like what makes most sense to you here?
Either type 1 or type 2 Cartesian.
Yeah, Cartesian type 1 or 2. This is definitely not polar. I would stay away from polar. So let's try and figure out. I think the easiest is just type 1 because our y's are between two functions of x, and our x's are between, it's I think obvious from the picture, between 0 and 1. So I know my x's are between 0 and 1. What are my y's between?
Y equals 1.
Y equals 1. So that'll be my upper limit, right? So that's
And
the top.
1 minus x.
1 minus x on the bottom. Good. And that's it. I mean, the setup now is pretty simple. You just go 0 to 1 here. That's going to mean dx is on the outside because that's my restriction on x. Then we're going to go from 1 minus x to 1. Those are my restrictions on y, so dy goes on the inside. And then what are we integrating? The density function, xy. There it is. There's the setup. Now, I'm not going to take you the rest of the way, but now you've got the integral, right? If you compute that, you'll get a numerical answer, and that'll give you the mass of that object, that lamina. Questions? How would this problem change if I told you that this lamina had uniform density? What would this density function have to be if it's a uniform density function?
Yeah,
1.
constant.
Just some constant. It could be 1, but it's going to be just generally just some constant. And so instead of integrating this, you'd be integrating some constant here, which we could pull out of the integral, right? And make that a 1. Come on. Can make that a 1, right? And so just out of curiosity, what would this integral be here without the c? What would it represent physically here?
Just the center of that.
What is the double integral? What I'm asking is, what is the double integral over d of 1 dA always equal to?
The area.
The area of D. So this is one of those things I told you is going to come up later. Don't forget, this is the area of D. So if this happened to have uniform density, if it was, it's not, but if it was, then this rho function would be a constant, which I could always take out. And this integral would just be the area of that region. And so all you'd be doing is multiplying the constant times the area of that region. That would be your mass. If it was uniform density, which it's not. And in Cal 2, I believe if your professor got to it, you may have done this already with mass, but I guarantee you did not do non-homogeneous, because in Cal 2, you only had single integrals, so you couldn't do this. You didn't have double integrals yet. Okay, moving on. So we have a way of finding the mass of the lamina, right? Now, after you learn how to do mass, you then learn how to find these other things called the moments. Now, this is a physics concept. You have the moments about an axis. So again, let's say you have a lamina. Let's say you're given the density function and you would like to find the moment of the lamina about the x-axis. By definition, the moment of the lamina about the x-axis is capital M subscript x. And do y'all see it's almost the double integral we just did? What's the only thing we've added to it?
Added one variable.
Yeah, we added the y into the integrand. So instead of it just being the density function, it's going to be the density function times y. And that's your moment about the x-axis. The moment about the y-axis, which is a different computation, is the same thing, except now you replace that with an x. Now, what is the moment? The moment of a particle is its mass times its directed distance from an axis. That's a physics definition. You want to know the moment of something. It's the mass of the object or the mass of the particle times the directed distance from some axis. So when we are talking about the moment of the lemma about the x-axis, we're saying if we take a particle here, we want to know its mass at that point, and then we want to know its distance from the x-axis, which will always be your y coordinate. And that's why you're taking y times the density. Well, actually this right here together is mass. And so it's your mass times your distance, and that gives you your moment. And then if you do the y-axis one, the only thing that changes is that now you're at that point, but now you're looking at this distance, and that's always going to be an x value. Okay. Yeah, I think, okay, so what about for this problem we just did? What if for this problem that we just did, what if I asked us to, instead of doing this, I said, find the moment about the x-axis? Only one thing would change, right? In the integral, I mean, everything else would stay the same. It'd be still 0 to 1. It'd still be 1 minus x to 1. But instead of having xy dA or dy dx, instead of having that, we would throw what in front here?
A y.
A y. It's always the opposite of the moment. If you want the moment about the x-axis, you put a y. If we wanted the moment about the y, then it'd be the same double integral, 0 to 1, 1 minus x to 1. Now we would have in here x, and then your xy dy dx. And these you could compute, and those will give you numbers, right? Okay, so we have this idea of a moment. So just to be clear, to get the mass, right? To get the mass of the lamina, you have to do some double integral. Once you have the mass, if you want to do the moment about the x-axis, that's a different double integral. If you want to do the moment about the y-axis, that's a different double integral. And then that finally brings us to the center of mass, which is what we're really, the whole goal of this whole thing was, is how do you find the center of mass of a lamina? So if you're given a lamina, how do you actually find the point in here that's your center of mass? And it's a point, right? This is a point. We call that center of mass the point x bar, y bar. And so we need some way of finding x bar, and we have a way of doing it. And then we need to find y bar. There's another formula for y bar. I'll show you that formula in a minute. Let's just look at what the formula for x bar is. To find x bar, all you have to do is take the moment about the y-axis and divide it by the mass. So remember, this is a double integral, and you're going to divide it by the mass integral, which is another double integral. They're not the same double integrals, though. So you basically have to figure out what this top one is. That's going to give you a number. You divide it by this bottom integral. It's going to give you a number. You divide those, you're going to get a number, and that will represent your x coordinate. So to find x bar, you have to do two different double integrals. To find y bar, it's the same thing. It's just a different formula. So to find y bar, you take the moment about x-axis and divide it by the mass. So if I asked you to find the center of mass of a lamina, if I asked you to do it, how many double integrals would you have to do?
Is it 6?
3.
Yeah, just 3. You need the mass double integral, and then you need the moment about the y and the moment about the x, and that's it. Because you use the mass for both, right? Do y'all see that? You do the mass for both. So you'll need the moment about y over the mass. That's 2 integrals. Then you need the moment about x. That's a 3rd integral over mass, but you've already done the mass. All right. So here's one. I think what we can do here. Oh my God, is it already 2:20? Find the center of mass of this region. What do you think? Do you think y'all can handle this? Do I need to go through a whole setup on this? Y'all okay? I don't think I want to go through this whole thing. We'll just run out of time. There's a few more things I want to talk about in this section. So you would, to do this, you would set up the mass integral, then the moment about y, and then the moment about x, and then you go find your x bar, y bar. I wanted to show you this though. I wanted to show you this region because I actually have a picture of this. This is what the region looks like. Okay, this is the lamina, but it has a non-uniform density. So it's more dense over here than it is over here. The darker means more dense, okay? Now, why is this just a double integral? The reason it's a double integral is because we can really visualize that density as almost like a height of a surface above it. You see, we can kind of visualize the ground as being the lamina. So there's my lamina. And then what I'm doing is at each point, I have a density. So if that density is big, it's just a height at that point. And as I move further over into the lamina, I have more density there. I have a higher point. And so really this does translate into just really the volume of some solid between two surfaces. That's why it's a double integral. I hope that that makes sense. In reality, this is just a flat sheet of paper, but you could visualize it as being a solid above a sheet. That kind of makes sense? Yeah? Okay. All right, so you have now the ability to find the center of mass of a non-homogeneous lamina. Then there's these other concepts in physics, something called the moment of inertia. The moment of inertia is basically an object's resistance to rotation. A good way to think about moment of inertia is, and I'm not here to go into a lot of physics here, but if you take like, I'm just trying to think of a way I can explain moment of inertia. Let's say that you have a door. Okay, here's a door. And let's say it's on, the hinges are right here. Okay, so you have a hinge here and a hinge here. And then you apply a force to the door to try and swing it, right? Along that hinge. The door has a resistance to motion, right? All objects at rest tend to stay at rest, blah, blah, blah. So there's this resistance to the rotation about this axis. And a measurement of that resistance is called the moment of inertia. If you were to take that same door, that's supposed to be the same door, but this time you put the hinge, and I know this makes no sense physically, but if you put the hinge right in the middle of the door and you apply a force, it will still have a resistance to rotation, but it'll have a different resistance than if it was hinged here. So your moment of inertia is all about the object itself and the axis of rotation, what you're trying to rotate it about. And so there's a way to calculate, give a numerical value to that force or that resistance to motion. And that's called your moment of inertia. And so we have a way of calculating it. If you want to know, if you're given a lamina that's non-homogeneous and you want to know its moment of inertia about the x-axis, that means if you had your axis of rotation here and wanted to rotate it, the moment of inertia, this calculation would give you a numerical value representing that resistance to the rotation. So do y'all see that it's basically the mass integral with y squared in front now instead of y? That's your resistance to rotation about the x-axis. If you want to know the resistance of rotation about the y-axis, that means instead this way, then you're going to have a different formula. And the only thing that changes here is that you have an x squared in front of the density function. So it's kind of like if I go back to this door, if I were to take like a third scenario where this would be like the y-axis here, I could also ask for rotation about the x-axis. So now your hinges are down here and you're rotating the door this way, right? That's going to have a different moment of inertia than rotating around the y-axis. I hope that makes sense. At the end of the day, it's just another double integral. You grind out the computation. It is what it is. There's also a third moment of inertia, and it's called the moment of inertia about the origin. And all it is just the sum of these two. It's just these two answers added up. Isn't the moment of inertia almost the same as the moment? The moment, right? The moment about the x-axis is this integral, but not y squared, just y. And the moment about the y-axis is this integral, but instead of x squared, just x. The moment of inertia is not the directed distance, but the squared directed distance. That's the difference between moment and moment of inertia. Okay, we're not going to get more into the physics here. Okay, that's it. And that's it for this section. So if you're going to do the mini exam, it does have a problem on there with center of mass and moments of inertia. All right, how are we doing here on time? In 10 minutes. Okay. At least I can get this set up in 10 minutes just to get you thinking. Triple integrals. So to get you kind of motivated thinking about this, as of right now, we have two scenarios that we've looked at. We have our standard Cal 2 integral. Now here in Cal 3, we have this idea of a double integral. And we're about to do triple, right? In Cal 2, our standard integral is something like this. Integral a to b, f of x, dx. This represented, take a function, started at a, ended at b, calculate this. This gives you the area right here, right? This area is represented here by that integral. Important thing that we talked about, I think it was last class, maybe when we first started double integrals, was to get you used to the idea that when you're looking at this, the domain here, what is the domain? What is our region of integration, I should say?
A to B.
A to B, right? It's all values of x between a and b. So do you agree that this domain is one-dimensional? It's one-dimensional. If I say, hey, look, all the values of x between a and b, you just think of a number line, right? You're just thinking, oh, I've got a number line. Okay, here's 0, here's a, and here's b. And I'm just talking about all the things between a and b. That's like a line segment, isn't it? That's one dimensional. With a double integral, what happens is now we go into three-dimensional space and we have some surface up here. And maybe there's a surface on the bottom of it too. And we're trying to find the volume of this thing. And so we look at the ground and we look at the shadow of this on the ground, right? That's the projection down to the ground here. That's our domain now, right? And that domain is going to have, you know, X between two things and Y between two things. And what, you know, these might be constants, right? They might be functions of X or functions of Y, might be polar, shit, we don't know. Double integrals in general could be a lot of different things here. But the main thing I want you to take away from this is that this is two-dimensional, right? It's two-dimensional. So whatever the D is on the ground, that D is something in the XY plane. So your domain is actually two-dimensional as opposed to over here where it's one-dimensional, right? One dimension is the domain. The two dimensions is the picture of the function. Here, two dimensions is the domain and three dimensions is the picture. So what do you think a triple integral is going to be? Let's just go straight to the domain. Let's not even talk about the picture. Let's just go straight to the domain. X has got to be between something, right? Y has got to be between something. And Z's got to be between something now, because you're going to have three variables. And so you're going to have a three-dimensional domain, aren't you? And so now, isn't your domain now here three-dimensional? Just some solid object in three-dimensional space? I'll reiterate this one last time. In the Cal 2, you pick an X value. That X value has to live on this line segment. Then you go in, you approximate the area of this rectangle. Here, you pick some XY in the region. You go to that XY and you draw a little box in here and you find the volume of that box. And that'll give you the volume under that one piece, and then you add them all up. Here, you're going to pick some point in this three-dimensional solid. It could be inside, it could be on the surface, it could be anywhere in it, right? Just anywhere within that solid. And you're going to take that point and plug it into a function. So what's the problem now?
Now we have to draw something in 4 dimensions.
Yeah, 4D, okay? Not happening. It's not happening. We've reached a point now where I cannot draw you what we are finding like the triple integral represents something, right? Like here, the double integral represents the volume of the solid between these two surfaces, right? Here, the double integral represents the volume of the solid between these two surfaces. Here, the integral represents the area of the region between two functions. If I had another function here, then it would be the area between, right? Here, this triple integral, whatever it is going to represent the what between two whats, right? Does that seem odd now? We can't visualize it, but we can still do it. And you might ask yourself, well, what's the value of something like that, right? Like, what's the actual value? Well, let's just go with what we just talked about. What if this solid, at every single point in this solid, what if I told you I could tell you the density at every point? What if I could tell you the density at every point in that solid? Then what would some sort of triple integral over this solid? Now, what do we call this solid? We call this over here D. This is our good old line segment. Here, we normally just call this E, our domain, so we don't confuse it with the D from the double integral. What would this triple integral over this density function, which is a function of three variables, with respect to question mark, what do you think this would represent then to us? Think about what we
mass
just
of
did.
the solid.
Yeah, just be the mass of the solid. That's it, right? So even though we can't visually like understand what's happening, it makes perfect sense if we extend what we've learned in 2D over to 3D. Now, I do need to clarify something here. Let me see here. Yeah, I'm not going to be able to get into an example, but back here, I'll do it in green. This little dx right here always represented this little infinitesimal little change in x, right? And then over here on a double integral, I forgot to put the double integral up here. Double integral over d of f of xy dA. The dA was this little infinitesimal box on the ground. It was this little tiny little box right here. And it's actually like normally this is dy dx, or it could be dx dy depending on our order of integration. And if we go to polar, it could be r dr d theta. It just all depends. I'll even put that here. It could be r dr d theta if we go to polar. But all that represents is the area of that little patch on the ground. So that's why we put dA. It's the infinitesimal area. Here we put dx because it's the infinitesimal change in x. What do you think I should put here? Because you're going to have a little point in here and you're going to have a little patch, but you can't have a patch in three-dimensional space. What would it be in three-dimensional space?
Infinitesimal volume.
Yeah, like a little infinitesimal box around your point. And so it would be with respect to V, volume, instead of with respect to A, and that will represent to us dx, dy, dz, or, oh shit, dx, dy, dz. Do you think we can change the order? Maybe. Like maybe this changes, maybe we could go dx, dz, dy, or maybe dy, dx, dz. How many of them would there be if I can change the order? Should be 6 different ways I could do this. Okay, I'm gonna do this formally. Okay, I'm gonna go through all this formula formally, but what I'm trying to get you to see is that we have now reached a point where we are not going to be able to visualize the actual functions. We are only going to be able to visualize their domains. Is that good or bad? I don't know. So we will start out next class by looking at the most basic domain we can have. And it goes back to like when we were doing double integrals, the first domain we had was if x was between 2 constants and y was between 2 constants. And we got a nice rectangle, right? Our domain was a rectangle. When we look at a triple integral, the most basic we can have is x's are between 2 constants, y's are between 2 constants, and z is between 2 constants. And in that case, our domain will just be a box. And then we're going to have to start adapting and getting it more complicated, type 1, type 2 type thing. All right, but we just don't have time for that today. So we will start triple integrals officially tomorrow. Hopefully that gave you some little insight into where we're headed. Good news, we don't do quadruple integrals. Okay, we don't. Because the domain of a quadruple integral would live in 4-dimensional space. So we wouldn't even be able to visualize it. But mechanically and mathematically, it makes perfect sense to do quadruple integrals. In fact, there is no limitation on how many integrals you could have. You could have 5, 6, 7, 8, but you just lose all visual connections to it.
Quadruple even have a purpose then?
Sure.
Other than just doing it?
Absolutely, because a quadruple, remember what it's doing. It's adding up an infinitely many things, right? That's what it's doing. So if you have some function, doesn't matter, you know, if you have some function f that has multiple variables in it, maybe this is a function that, I don't know, I'm just going to talk about, it's probably not going to make sense in what you're thinking of here, but like, let's say this is something that predicts the probability of rain today. So maybe it takes in like the temperature, the barometric pressure, the humidity, the blah, blah, blah. It takes all these things out and then it spits out some number that represents the spits out some number that represents the probability of rain for that day. So it's going to spit out some number between 0 and 1. Okay. Then what could you tell me about the, how many variables? 1, 2, 3, 4, 5, 6, 7. And I don't even know what to call the domain region. I'll just call it, I don't know. Let's just call it capital P because I haven't used that variable of this function with respect to, and I can't call it volume. I just call it capital H for like hypervolume or something like that. What would this have to be equal to? So if this function gives you the probability of rain at every, with all these different conditions, right? And that probability would have to be between 0 and 1. What should the sum of all probabilities be equal to? No? It should be equal to 1. So think about it like this way. If you roll a die, right? You roll a die, you have, what are the chances of getting a 1, a 2, a 3, a 4, a 5, and a 6, right? There's 1/6 chance of this, 1/6 chance of that, 1/6 chance of that, 1/6 chance of that, 1/6 chance of that, and 1/6 chance of that. This is the probabilities, right? Of each of those events. The sum of all the probabilities of every possible event should always equal 1. So this, what, 7 integrals of the probability function should be 1. I'm trying to show you that it just, you can extend this even though there's no geometric meaning to it. It can have physical meaning still. All right, we are 2 minutes past, so I appreciate your time. I'd say make sure you try and do your homework that goes with everything through polar coordinates, and then get working on those take homes if you're doing them. Take home one. Any questions? Okay. Call it a day then. Have a good one, everyone. I'll hang out for a minute if you have a question.